Welcome, everyone, to this explainer. Today, we're unpacking something that literally impacts the bottom line of almost every modern business out there, the structural integrity of your software. If you're an executive overseeing major tech projects, software development can kind of feel like this expensive black box, right? One that occasionally gives you major heartburn. Well, today, we're opening up that box. We're going to focus specifically on the absolutely crucial business implications of testing object-oriented software. Okay, let's dive into this. Why do software bugs cost so much more the later you find them? It's a fundamental question about hidden project risks. Look, when a structural flaw makes it all the way to launch day, fixing it isn't just a quick tweak to a few lines of code. No way. It can mean tearing down months of hard work, totally derailing your time to market, and blowing up your budget exactly when the pressure is at its absolute highest. As our sources explicitly state, the sooner problems are detected, the easier and cheaper they are to fix. You see, modern object-oriented software promises this incredible speed, reusability, and flexibility. But actually, that speed is kind of a double-edged sword, because without early, rigorous validation, these hidden structural flaws just get baked right into the core of your product, severely threatening your budgets and timelines down the road. So here's our roadmap for today. We'll start with the business case for testing, then inspect bricks versus walls. We'll explore the inheritance risk factor, polymorphism, and predictability. Take a look at automated state machine inspectors, and finally, wrap up with protecting your timelines and budgets. Let's jump right into Section 1, the business case for testing, mitigating architectural risk. It is definitely time we stop viewing testing as just some technical afterthought or like a final checklist right before a product ships. In the object-oriented world, testing is a strategic business necessity. The experts in our source material have a very clear motto for this: test early, test often, test enough. In the old days of traditional software development, system testing mostly happened right at the very end. But with object-oriented technologies, decisions about testing really can't wait. It has to begin early, even before the code is fully written, and be tightly intertwined with development. This iterative process is genuinely the only proven way to safeguard your project's financial health. Moving on to Section 2, inspecting bricks versus walls, the scope of OO testing. To really grasp the risk here, we have to understand how object-oriented testing is completely different from the traditional software checks you might be used to. Think of your software as a building. In traditional programming, testing a unit, like a single method, is basically like inspecting a single brick. If the brick is solid, great. But object-oriented programming is built on what we call classes. A class is a complex abstraction of data and behavior. So testing a class isn't just looking at one brick. It's literally stress testing an entire load-bearing wall to see how all those individual bricks interact. If a class implementation is wrong, every single room relying on that wall is going to behave improperly.
Section 3, the inheritance risk factor, bug propagation.
Now, what's really interesting about this slide is how it illustrates inheritance. Inheritance is incredibly attractive because it allows for massive code reuse and speeds up development. But from a business perspective, it's a double-edged sword, introducing severe downstream risks. Think of Class A, here, as the foundational blueprint for our software building. It lays down the essential code defining how things should work right at the ground level. So when developers create a new class, let's call it Class B, that inherits from Class A, they don't have to rewrite all that foundational code. They reuse it. In our building analogy, they're essentially constructing a brand new floor squarely on top of that existing foundation. It's super efficient, right? Well, here is the massive risk. Inheritance creates a direct pipeline for bugs to propagate from a parent class down to all of its descendants. If there's a hidden flaw down in that foundational Class A, that flaw is instantly inherited by Class B and Class C and so on. An untested foundation causes bugs to spread downward rapidly. By testing a class as it's being developed, you're eliminating faults early and preventing a complete collapse of the application later on. Section 4, polymorphism risks, managing predictability. If inheritance is the first big technical challenge, polymorphism is the second. Polymorphism is simply the ability to treat an object as belonging to more than one type, which allows for incredibly flexible system extensions. To translate this back to our construction analogy, imagine having the ability to seamlessly swap out building materials, like replacing a standard brick with a reinforced steel beam on the fly, without stopping construction. In the real business world, this is like swapping a standard credit card processor for a brand new crypto payment gateway without taking your checkout page offline. It's powerful stuff. But as an executive, you have to consider the business consequences. Because the exact class of an object might not actually be known until the program is running, you can get all these unanticipated interactions. If a developer swaps in a new object type, it absolutely requires rigorous retesting of both the parent and child structures to ensure they still play nice together. Unmanaged polymorphism increases possible interactions exponentially. We're talking massive potential for systemic failures and very costly launch delays.
This brings us to Section 5, Automated State Machines. Continuous inspectors.
We've looked at the problems, but what about the solutions? Well, because an object-oriented system is so dynamic, driven by countless paths through the code, manual testing just cannot keep up. You need continuous digital building inspectors. And this brilliantly illustrates how automated state machines do exactly that. They tirelessly track the entire lifecycle of an object, from the moment it's created, through its various states, right up until it's destroyed. Tools like Object Time allow your teams to literally animate design diagrams and simulate complex scenarios automatically. They validate inputs based on an object's current state and dynamically check the outputs. Basically, these automated tools are running continuous stress tests across all those tricky polymorphic interactions. By simulating these scenarios 24/7, they significantly reduce the manual labor and the tremendous financial cost of hunting down deep structural bugs late in the game. Section 6, Protecting Timelines, Securing Budgets. Let's bring all these concepts together for the real business payoff. So the crucial point is this. The old way, waiting until the end of development to integrate and test, results in crazy high costs and delayed timelines. The object-oriented way requires a total mindset shift to early and incremental testing. When you understand that you're testing load-bearing walls, mitigating inheritance risks, and managing polymorphism from day one, you realize massive cost savings and actively squash project risk. I'll leave you with this final thought to ponder. Does your current testing budget reflect the true cost of a structural software failure? Object-oriented software really is the backbone of your digital business. Testing it isn't just some arbitrary downstream expense. It is a critical, upfront investment in the structural integrity of your company's future. Thank you so much for joining me for this explainer, and I hope it helps you look at your next development project through a totally new lens.